Welcome to The Explainer. Today, we're jumping right into a totally wild connection between two completely different worlds. On one hand, you've got the massive, high-stakes arena of global geopolitics and energy supply. On the other, the invisible, microscopic world of modern electronics. Now, I know it sounds a little crazy at first, but by the end of our time together, you're going to see exactly how a massive geographical choke point operates using the exact same mechanical philosophy as the tiny components powering the device you're using right now. It's a fascinating story of scale, power, and flow.
Okay, let's kick things off with a staggering fraction, 1/5. That represents the amount of the entire world's oil supply that passes through one single, incredibly narrow waterway on our planet, the Strait of Hormuz. Every single day, a massive fleet of giant ships carries essential energy from the Middle East to the rest of the globe right through this tiny geographic bottleneck.
Think about the sheer scale of that dependency for a second. If this passage stays open, global trade hums along, economies grow, and life just continues as normal. But if it closes, everything changes. The stakes literally couldn't be higher. This single geographical feature dictates the flow of global energy. It is the ultimate choke point.
Part 1. Enter the transistor. So let's take that immense scale, the oceans, the giant tankers, the global economy, and shrink it down. Way down to the microscopic level. Because the foundational building block of our modern digital age, the transistor, works in a surprisingly similar way. Just to strip away any of the intimidation factor here, a MOSFET, the most common type of transistor, is simply a tiny semiconductor device. That's really it. And just like we saw with our ocean strait, the whole thing relies on flow. But instead of thousands of tons of oil flowing through a physical sea route, we have electricity flowing through a microscopic channel.
Part 2. Mapping the analogy.
When we map these concepts together, the complex engineering inside your computer actually becomes incredibly intuitive. It's amazing how perfectly these two domains map one to one. Let's look at the physical side first. You have the Persian Gulf, right? That's where the oil ships begin their journey. Well, in our electronic transistor, that exact starting point is called the source. Next, the ships want to reach the open ocean to deliver their cargo. In our transistor, that destination is called the drain. And finally, those physical oil tankers moving through the water, they are the exact equivalent of the electrical current moving through our tiny silicon channel. The ships are the electrons, starting at the source and trying to reach the drain.
Part 3. The power of the gate.
But here's the thing. A route is really just a route until somebody or something is actually in charge of it. You need a control authority to govern the flow of these moving resources. Otherwise, it's just chaos. And this brings us to the most vital part of the transistor, the gate. Think of the transistor's gate as the ultimate control authority. For the sake of our analogy, imagine a fictional, completely neutral political leader sitting in a control tower overlooking the Strait of Hormuz. Their sole job is to make the call on whether the shipping route remains open or gets restricted. Just as that leader's decisions influence physical shipping traffic, the transistor's gate strictly controls whether electricity is allowed to flow from the source to the drain.
So the crucial point is what happens when we pull that permission. When the gate receives no control voltage, when it's officially turned off, that electrical channel simply does not exist. There's no path, there is zero current. It is exactly like a closed shipping lane where the governing authority has ordered all traffic to stop and absolutely nothing can pass through. A total shutdown.
But now, flip that script. Turn the gate on, and you get this beautiful 1, 2, 3 sequence. Step 1, enough voltage is applied to the gate, representing our control authority, giving the green light. Step 2, almost like magic, an invisible conductive channel instantly forms inside the transistor. And step 3, current flows freely from the source to the drain. It acts just like ships suddenly being allowed to move smoothly and swiftly through an open, unrestricted strait.
Part 4. Changing the world. You might be wondering, why is this simple act of turning a microscopic channel on and off such a massive game changer? Well, the reason transistors completely revolutionize human history comes down to this concept called the lever effect. The absolute brilliance of the transistor is that the gate itself carries almost no current. A tiny, incredibly weak electrical signal applied to the gate can control a vastly larger current flowing from the source to the drain. Think about the scale of that power for a second. It is exactly like a single person lifting a tiny finger to press a small switch, and in doing so, opening a gigantic, roaring floodgate. One tiny command dictates the flow of a massive stream. Now, take that insane leverage and scale it up. We aren't just talking about one strait or one gate anymore. We are talking about billions.
Modern processors contain billions of these microscopic electronic gates packed onto a piece of silicon the size of your fingernail, and each one of them is rapidly making these exact on and off decisions billions of times per second. Together, this massive synchronized armada of tiny gates dictates absolutely everything in our modern digital lives. Every time they allow current to flow or force it to stop, they are processing information. Those microscopic decisions perform every single calculation inside your smartphone, your laptop, your gaming consoles, and the massive AI computers shaping our future. All of it, literally the whole shebang, relies on the simple principle of a gate opening and closing a channel. So, as we wrap up this explainer, let's just look at these two vastly different worlds side by side one last time, the macro and the micro. The Strait of Hormuz controls an essential global energy route, moving physical oil. The transistor controls an essential electrical route, moving invisible electrons. They exist on entirely different scales of reality, and yet they rely on the exact same mechanical philosophy.
It really all boils down to this singular, powerful thought from our source material. Control the flow, and you control the system. Whether you're directing thousands of massive cargo ships across the ocean or billions of electrons across a computer chip, the one who holds the gate holds the power. It really makes you look at the hidden architecture of the world a bit differently, doesn't it? So I'll leave you with this question to ponder. What other invisible flows in your everyday life dictate the complex systems you rely on without even realizing it? Thank you so much for joining me on this explainer, and definitely keep questioning the systems around you.